are alkenes? Alkenes are hydrocarbons with at least one carbon to carbon double bonds. Not necessarily that all the bonds are double. If it has one, then it's an alkene. The rest can be single bonds. But if it has one, it becomes an alkene. So they are said to be unsaturated hydrocarbons. And the word unsaturated was used in Form 1 to mean a substance that does not contain the maximum amount of solute that it can dissolve. So we are not going to use that in this particular topic. We are going to say an unsaturated substance is one that contains a carbon-to-carbon multiple bond. That is our definition. Forget does not contain enough. Of course, it is true it does not contain enough. If a compound has 2 carbon atoms, it can hold 6 hydrogen. It's true it doesn't contain enough, but that is not used as a definition here. So the definition for unsaturation is the substance that has carbon-to-carbon multiple bond. That is our definition. And we can give a few examples. We have the very first of them that consists of 2 carbon atoms. We can redraw it, and then it has a double. Note again that we don't have an alkene with 1 carbon atom. It doesn't make sense. How do you have a carbon-to-carbon double bond if you have only 1 carbon? So the simplest of the alkene will have 2 carbon atoms. So let's put the hydrogens 1, 2, 3, 4, 1, 2, 3, 4. So that is the first one. That's the first alkene. So note that I've put them with counting. Now let me redraw this one. 1, 2, 3. Now put the double bond right there. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So that is the next one. So we've already said that alkenes will have an adding in. So ethene, propene will be that. So the general formula of the alkenes. Now to obtain an alkene from an alkane, what have I done? So this is ethane. I have removed that and removed that so that I can make a double bond. I need 2 electrons. This electron that was used here, bring it back. This electron that was used here, bring it back. Then use the 2 to make a double bond. So I have to remove 2 hydrogens so that I can put a double bond. So the general formula therefore becomes Cn H2n plus 2 minus 2. The 2 that I have to remove. So that will definitely go. So I have CnH2n as the general formula of the alkanes. Note that n starts from 2 and not 1. So if I want the molecular formula of the 6th alkane, it will be C7. Yes, C7. Why? Because the first one is C1, C2. The first is C2. So the 6th will be C7. Will be C7. That I think is important to note. The simplest has 2 carbon atoms, so the 5th will have 6 carbon atoms, the 6th will have 7. Write it down. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Then I can put the double bond either there, I can put it anywhere. Then 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Don't be in the bad habit of not putting the hydrogen. I want to do the skeletal formula. 1, 2, 3, 4, 5, 6. Then the double bond is right there between the first and the second carbon atom, and that will be hexane. Wrong. Why is that wrong? Because I can put the double bond there, I can put the double there. So I must specify where the double bond is. How do I specify? As usual, use numbers. 1, 2, 3, 4, 5, 6. So this is 1, 2, 3, 4, 5, 6 is hex. 1, 2, 3, 4, 5, 6. So I can say the double bond is either on 1, 6, 2, or 5. So I use the lowest possible number. And the lowest possible number is 1. So hex1 is the correct name of that. Now I can draw another structure. Of course, with 6 carbon atoms. 1, 2, 3, 4, 5, 6. Now put the double bond right there. So that is 1, 2, 3. So hex 3, hex 3e. Now this and that have the same molecular formula, but they have different structural formula. One name for that, same molecular formula, different structural formula. I hope you have said isomers. Yes, they are isomers. But this time that's another type of isomerism that we call positional isomerism. Positional isomerism. They differ by the position of the functional group. So the alkenes will exhibit branch isomerism where we have a branch. So we remove this and put it here. Remove one carbon and put it there. That will be a branch. Then we'll also have positional isomerism that differ by the position of the functional group. So to name alkenes, the name must end with in. If it is branched, then the rules will apply as they applied for the alkanes. Those rules, the longest continuous chain, the branch and all that we said. But what you must take note of is that the longest continuous chain must contain the double bond. The longest continuous chain must contain the double. For instance, the structure I have here, the longest continuous chain has 1, 2, 3, 4, 5. But the longest continuous chain containing the double bond has 1, 2, 3, 4 or 1, 2, 3, 4. So I use the one that has 4. Then the other thing, the double bond must gain preference. You must give it the lowest possible number. So this compound is going to be 1, 2, 3, 4. So but 1 in, because the double bond must take the lowest possible number. Then it has a branch on carbon number 2. So 2 ethyl. 2 ethyl but 1. 2 ethyl but 1 in is the name of that. So the longest continuous chain must contain the double bond. Must contain the double bond. So then we have talked about positional isomerism. So they differ by the position of the functional group. In this case, the double bond. So we said to do that, you must rotate. You must rotate the. So you only are allowed to talk of ethene and propene. You cannot talk of butene. You must talk of either but 1 in or but 2 in. Butene is wrong. It's wrong. So you have to specify where the double is because there is ambiguity. It can be on the first or can be on the second. How do you prepare alkenes in the lab? They are prepared by a process that we call dehydration. The removal of water. To dehydrate means to remove water. And there are two major dehydrating agents, that is sulfuric acid and aluminium trioxide. Now we've come across the sulfuric acid as a dehydrating agent. It dehydrated sugar, it dehydrated oxalic acid to form carbon 2 oxide, carbon 4 oxide. It dehydrated methanoic acid to give you dehydrated copper sulfate to give you anhydrous copper sulfate. It's a dehydrating agent. So if you subject ethanol, for instance, ethanol, we shall come across these compounds. Ethanol you subject to sulfuric acid and the temperatures are critical. At 180 degrees Celsius, you will remove water. You remove water. So when you remove water, minus H2O from this, so you remain with carbon, 2 carbons, right? There are 2 carbons. You're not removing any carbon. You have removed from the 6 hydrogen. You have removed 2. You remained with 4. Then of course you have this water here. That water. I've just subtracted so that I can show us what exactly is happening. So the water, you can dehydrate alkanols to alkenes. You remove water from alkanols and you get alkenes. So at temperatures above 180, if you use temperatures below 140, the product is not going to be an alkene. It is not going to be an alkene. Note that in the process, you can dehydrate this alkanol completely to carbon. Sometimes it happens, so that the mixture will turn black in color. When that happens, the carbon can react with sulfuric acid because apart from being a dehydrating agent, it is also an oxidizing agent. So it can react with that to form carbon 4 oxide and sulfur 4 oxide. Now that means that the gas that is produced, ethene in this case, will contain carbon 4 oxide and sulfur 4 oxide impurity. These need to be removed, and it's very easy because all you need to do is to bubble the resultant gas through sodium hydroxide. Sodium hydroxide will react with all these. It will absorb the carbon 4 oxide, will absorb the sulfur 4 oxide. That will leave you with the pure ethene. The physical properties of the alkenes are similar to those of the alkanes. Why? Because again they are non-polar, they don't dissolve in water. They also melting point and boiling point will be size dependent. They don't depend on the size because they are van der Waals between the molecules and the surface phenomena. The chemical properties is what I need to look at now. So what do alkanes burn to? Alkenes will burn to carbon 4 oxide and water. They will burn to produce carbon 4 oxide and water. So remember again, combustion involves the addition of oxygen. Oxygen must be added. Don't just leave. It is not cracking, it's combustion. So to get carbon 4 oxide and H2O, so I can balance the 3 carbon, again the 6 hydrogen, that gives me 7. So remember what we did, 7 over 2. So multiply out by 2 to get 7, to get 6, and to get 6. That is what you get when you burn. So you can also get carbon 2 oxide if you are working limited supply of air. But the one thing that now needs to be noted is that irrespective of the size, the frame will be yellow and luminous. So even ethene. You may have paid a visit to a Juakari artisan, the ones that uses gas for welding, and you look at the frame that they are using before they turn on the supply of oxygen. The frame that they have there, it is usually very yellow and sooty and luminous. Why is, and yet what they are using is simply ethane, a substrate 2 carbon atoms. Here it's burning a sooty frame. So all unsaturated substances will burn in a sooty, luminous, yellow frame. That is all. That is final. It doesn't matter how long it is. For the alkanes, remember, if it is short, it will burn in a blue frame. If it's long, that's the time it burns in a luminous frame. But for the alkenes, all of them will burn in a sooty frame. But the next, the most characteristic reaction of the alkanes is what we call the addition reaction. In addition reactions, molecules just combine to form one. 2 molecules. It's like you start a football match and some people are not around and you cannot. Nobody wants to join in. So what happens when somebody comes in and they want to play? They just come and join. So that is an addition reaction. So generally in an addition reaction, this is what will happen. If you start from an ethene, for instance, and then you are adding a substance AB. Let me even use propene because I want to demonstrate something here. Now you add a molecule AB to propene. The first thing that will happen is that this bond is going to be broken. So what do you get when you break that bond? You get something that looks like that. It's something that looks like that. What have I done? Just broken that bond. Written this the way it is. It has 2 carbon. This one has only 1 carbon. Then you also break this bond. Then you add the AB across. One there, the other one there. A there, B there. All A there, B there. Not A and B on the same. Wrong. A, B there. Wrong. That can't happen. Can't happen. So you cannot add A and B on the same carbon atom. That will be illegal. Again, that's another thing that is very evil. Now you can also not get the A on that, and then you add the B there. That is also very wrong. It is punishable by sending to the guillotine. So it cannot be so far apart. So it has to be on one and the next. A here and B there, or B there and A on the other. So we have several steps that we can add, and whatever you are adding will determine the type of reactions. You will name the reaction depending on what we are adding. So for instance, hydrogenation. Hydrogenation is the addition of hydrogen. The condition for hydrogenation is nickel catalyst at temperatures between 150 and 250 degrees Celsius. That has to be remembered. So you hydrogenate using nickel catalyst. So what is formed is an alkane. What is formed is an alkane. Let's hydrogenate propene. So plus hydrogen. What do you need? A nickel catalyst at temperatures between 150 to 250. And what do you get? So let's rewrite the thing just as it is. Alright, hydrogen is right there. That is it after I've broken the double bond. Then I attach this hydrogen across it. Of course, it's not going to be different now. So that is what I get from hydrogenation of propene. Now remember, this is a reaction that we used in Form 1 when we are talking about the uses of hydrogen in hardening oils, converting oils to fat.
One of the industrially significant examples of addition reaction is the hydrogenation reaction of vegetable oils, which contain unsaturated hydrocarbons having double bonds. In the presence of a nickel catalyst, hydrogen gets added onto the unsaturated hydrocarbons, and they are converted into saturated hydrocarbons. This reaction converts vegetable oils into margarine.
Reaction is a halogenation. So as the name suggests, we are adding a halogen. Halogens are the group 7, fluorine, chlorine, bromine, and iodine. And you added a halogen to alkanes. So that is a substitution, a halogenation substitution. So substitution halogenation. This is a halogenation that is an addition. If you add a halogen, now there are two ways in which you can halogenate. You can halogenate when you dissolve the halogen either in an organic solvent or in the pure form. You don't need any sunlight for that. It's not necessary. The reaction will just take place. So for instance, let me add chlorine to that, and let me add bromine. Let me add bromine and dissolve it in tetrachromethane. So because what you'll be told is that bromine in tetrachromethane. So some students will go on to add the tetrachromethane, yet they do not remember that the tetrachromethane is simply a solvent. So what do I get? Again, the first thing I need to do is break the double bond and obtain the structure just as it is, without double bond, without just breaking this. So the first carbon has 2 hydrogen, second one has only 1 hydrogen. Then I attach 1 bromine there, the other bromine there. So I get 1,2-dibromopropane. Again, 1,2-dibromopropane. That is the product. So note that you don't put the bromine on the same carbon to get 1,1. You don't add the bromine on the one. It cannot become a 1,1,3. It is 1,2-dibromopropane. Now, but the most interesting reaction, halogenation reaction, is the halogenation with the solutions of the halogens in water. This one will not take place with the alkanes. You cannot halogenate alkanes with bromine water. Bromine liquid, yes, in the presence of sunlight. But bromine water is a bromine dissolved in water. That will not that reaction cannot take place. So, but the alkenes can be halogenated with the bromine water and the chlorine water. How does this reaction occur? So when you dissolve bromine in water, it will form hydrobromic acid and bromic 1 acid. Bromic 1 acid. If it's chlorine, it will form hydrochloric acid and hypochlorous acid or chloric 1 acid. Remember we said quite a bit about those things, that hypochlorous acid is a breaching agent, it is unstable, and you remember the chemistry right there. Now this one is already aqueous and ionized into hydrogen and bromide. It cannot react. But this one is molecular. It is in form of in fact, it is due to this one that we have that the solution is colored. It is due to this that this solution has either a yellow or an orange color because it is molecular. Otherwise, if it was ionized, it will be OH and bromide, none of which is colored. None of that is colored. The fact that it's colored means it is formed in form of a molecule. Therefore, it can combine with the alkanes. For instance, I will add now that to HOBr, the bromic 1 acid, bromic acid we said will not react. Bromic 1 acid can react here. So what do? Break the double bond. I have done that, broken the double, then I attach OH on one and Br on the other. Now this is what we call an alkanol. This is an alkanol, it has an OH. So it is 2 bromoethanol. 2 bromoethanol is what you get. But most importantly is that the alkanol is not colored, yet this one was yellow. So the bromine water will change from yellow stroke orange to colors. And this is used as the test for unsaturation. Any substance that decolorizes bromine water is unsaturated. Because saturated substances will not react with bromine water. They will react with bromine liquid, but do not react with bromine water. So you have a test tube that contains some substance here. Add bromine water. 2, 3, 4. Decolorized. It must be unsaturated. It remains orange. It remains yellow. It is saturated. It doesn't have multiple bonds.
On the left, I have an alkane molecule. In the middle, I have an alkene molecule, and on the right, I have a fairly concentrated bromine water solution. First, I'm going to use a pipette to put some bromine water into the alkane molecule. You can see that the bromine water turns it a dark yellow color. Now let's do the same thing with the alkene molecule, begin shaking it. The yellow bromine color will slowly begin to disappear until it's all gone. You are now left with a cloudy white liquid. Put this back in your test tube rack and let it settle out for a little bit. Here are the two test tubes side to side.
Now next, hydrohalogenation. As the name suggests, we are going to be adding a hydrogen halide. We're adding hydrogen halide. So we will just do that with an example. This is a propene plus hydrogen chloride, not hydrochloric acid. The moment it's dissolved, no way. So the gaseous hydrogen chloride. So we can break the double bond. Okay, where was the double? It was here. But doesn't really matter where I put it. So that is what I get when I break the double. Then I can put the H there and the Cl there. Alternatively, I can break the double bond again and then put the hydrogen there and the chlorine there. So there are two possible products. That is 1 chloropropane or 2 chloropropane. Now from observation, the main product is this, the 1 chloropropane. The rule therefore becomes hydrogen attaches itself to where we have more hydrogen already. To those who have, more shall be given. So this carbon has 2 hydrogen already. So a hydrogen will get there. Because this one has only 1. Hydrogen will not prefer to get here. It will be lonely. If you want to get where we have more of its type, so the hydrogen attaches itself to where we have more hydrogen already. So this becomes the main product and not the 1-chloro. Oxidation. In oxidation, what are we doing? We are reacting it with an oxidizing agent. Not like the combustion reaction, where that was also oxidation, but it was destructive. In this one, we are oxidizing. We are oxidizing with an oxidizing agent, that is potassium manganate 7. Potassium manganate 7 is what we are using to oxidize. So, but in this case now, so we shall consider ethene, and we add an atomic oxygen from the oxidizing agent. Oh, and we have a scenario here because we have been adding AB. We have been adding AB. I don't have 2, so where do I split? I don't have a place to split. So what will happen is you will combine that and you get something that looks like that. Oof! Yes, that is what you get. Now this is what we call an epoxide. An epoxide is a very unstable species. It's very unstable. What makes it so unstable? The bond angle, that bond angle, that bond angle. It makes it very unstable. So it will immediately break down, and when it breaks down, so this one will carry the 2 electrons. The 2 electrons that were used to bond here will be carried to the oxygen. So you'll get that as negative, and that is positive. Why? It has lost electron. Then water contains, because you have water, the permanganate will be dissolved in water. We'll have H and OH. So this one will bond there, or negative and positive. Bond there, this one will bond there. So what do you have now? OH, OH. Now this is what you call a diol. A diol, of course, is an alkanol that have 2 OH. It has 2 OH. So that's a diol. That is what you get when you oxidize alkenes. Now there are 2 common oxidizing agents. That is potassium manganate 7 and potassium dichromate 6. Potassium dichromate 6. But potassium dichromate 6 is a mild oxidizing agent. Doesn't oxidize alkenes apart from ethene. It only oxidizes ethene. With ethene, it will change from orange to green, but no other alkene will manage to be oxidized by the potassium dichromate 6. So note that the change in color is because the permanganate ions change to manganese 2. Manganese 2 is a colorless. It is actually colorless, whereas the manganese 7 is purple in color. Next reaction, and that is the hydration, the addition of water. We are adding water. So water, H2O shall be represented like that for the sake of this reaction. So we shall attach H on one and OH on the other. There are 2 ways you can do that. You can do that using Kong sulfuric acid. So let me start with the alkene, and I'll represent Kong sulfuric acid like this. Sulfur, okay, this the erroneous way of representing sulfuric acid. Now I will take this OS O 1 2 3 H. I will represent it like that. So just at this point, then combine the rest. So take that hydrogen, that bond, then combine this part to this O that is attached to sulfur, then this attached to 3 and all that. So I will combine that with H, OSO3H, and what do I get? Break the double bond. Thank you for breaking the double bond. Then attach H here, and attach OSO3H on the other. So this is called an alkyl hydrogen sulfate. Hydrogen sulfate is that ion. That's a hydrogen, sodium hydrogen sulfate. Yeah, that's not chemistry. That is elementary chemistry. So that's a hydrogen sulfate. Then this one we said when an alkane loses hydrogen is an alkyl. So that is an alkyl. So ethyl hydrogen sulfate is the name of that. So the ethyl hydrogen sulfate can be boiled with water now. OSO3H plus water, the sulfuric acid will be regenerated. So what's this H and OH? The H returned here.
The addition of sulfuric acid to alkenes occurs by a mechanism similar to the addition of hydrogen halides or water. In this case, the reaction products are sulfuric acid esters, known as alkyl hydrogen sulfates. The main difference between this reaction and the addition of water is that in this case, the process occurs so readily that the reaction mixture has to be cooled. An example of the addition of an inorganic acid to an alkene is the reaction between sulfuric acid and ethene. The product that forms, ethyl hydrogen sulfate, is an unstable compound. On heating in an aqueous solution, it decomposes by hydrolysis into sulfuric acid and ethanol. For many years, this reaction was used for the manufacture of ethanol on an industrial scale because of the low energy consumption needed.
The polymerization reaction, and what shall rightly be referred to as a self-addition. Now, what do you mean by that? If you start by the simplest of the alkenes, that is ethene, then you heat ethene. The double bond will just break, that is, of course, you heat under pressure, and the electrons will move in various directions. So the electrons that were used in making this second bond will break, and one gets there, the other one gets there. So you get a structure that looks like this. And now that you have made a such in the mixture, so let me just draw to illustrate what will actually happen. So the two will join via that electron that came from that. So they'll join, and the process can continue this side and continue the other side. That is what we call addition polymerization, because at the end of the day, you are going to get a wrong molecule. You are going to get a large molecule, a very wrong molecule consisting of small repeated units. That is what we call a polymer. So a polymer is simply a wrong molecule consisting of short repeated molecules. So the process through which polymers are obtained is called polymerization. And to name a polymer, all you need to do is to add the word poly before the name of the monomer. So we have heard of polyethylene, but correctly, when you name that correctly, it is supposed to be polyethylene. Polyethylene. Note that the resultant substance does not have a double bond, but it retains the E in ethene, because the rule is just add the word poly before the name of the monomer. So we call that polyethylene. We have other examples of addition polymers.
In this video, you will learn how to write equations for the formation of both polychloroethene and polypropene, as well as uses for both of these polymers. Start by quickly reviewing the polymerization of ethene. Here is an ethene molecule in a row, and under high pressure the double bonds break and the remaining molecules attach in series to form a long-chained polymer. To write this in equation, we would show this, where n represents a large number of molecules, and the square bracket shows the repeating unit. Here is the molecule chloroethene. Based on what we have recapped, pause the video now and try and write an equation for the polymerization of chloroethene. Here are chloroethene molecules in a row. Now let us break the double bond and join these molecules together to form a polymer. Writing this as an equation, we must show N molecules of chloroethene and the repeat unit of the polymer as shown. Polychloroethene is a very commonly used polymer, and it is likely you will have heard of it by its old name PVC, polyvinyl chloride. It is used in plastic PVC windows and doors, and it is also used in pipes, signs, and even in clothing. Polypropene is our next polymer. Pause the video now and draw the structure of the monomer for polypropene. Some of you may even wish to attempt the equation for the polymerization of this molecule. Hopefully, you will have drawn propene as the monomer. Exactly the same process occurs. The double bond breaks and the polypropene is formed. Here is the equation for this reaction. Polypropene is strong and is also resistant to fatigue, which makes it extremely useful for plastic hinges such as those on drinks bottles. Polypropene is also quite resistant to temperature, and therefore it is often used in medical equipment that needs to be autoclaved, and also kitchenware that may be put in a dishwasher. It is also used to make pipes, containers and bottles.
Like polychloroethene. Well, what is polychloroethene obtained from? It is obtained from chloroethene, because as you just said, we just add the word poly before the name of the monomer. So polychloroethene will be obtained from chloroethene, And how will that polymerization occur? As you have just said, the bond will be broken. You break that, bring that electron to that side and the other side. Then the result is something that looks like this. H with a chloro there, with a H there, and we can just close that and put an N there, showing that that will repeat in both. That will be repeated N times. So N of that will form a molecule like that. That's a very long molecule. Now, polyphenylethene, on the other hand, or what is also referred to as polystyrene, will consist of something that looks like that, or what we can call phenylethene, phenyl, as opposed to vinyl, because polychloroethene is also called polyvinyl chloride. So this can also be called a vinyl chloride. So how does the polymerization occur? So again, break the double bond, and you get the electron there, and then you have a H, and the benzene ring, so we call it. So again, I put the electrons there, like that. Then I can join, and I can continue out this side and continue the other side. Now the other example on this is so it is possible to polymerize all alkenes. Propene. How does propene? Now this is an interesting concept altogether. Now, because the structure, that is how propene looks like. So how does it polymerize? Now, if you break this bond, the electron will be there, the other electron will be there. So when you join the molecules, you are supposed to join this on this carbon and the other carbon, not this carbon. So you must join at this point. So how do I go about it? I just need to bend this molecule. I'll bring this CH3 at that point. Then I will have that is what now will join. That is what I will join. Not that whatever polymer you're going to get will contain a repeated CH3. After every CH2, there'll be a CH. Unlike what most students will do, they'll move this electron to that and then move that. That is not possible. You cannot replace. You cannot move this hydrogen here so that you can bond at that point. Addition, polymerization. The structure must be arranged so that it looks like ethene. So A, B, C, D. So you must rearrange it so that it looks something like that. For instance, to polymerize but2-ene. I want to polymerize but2-ene. So I have just been told that this is where the bonding is going to take place, on this carbon and the other carbon. So in order to join them and to facilitate the joining, I'll have to rearrange this, bring this here, and bring the other one here. So it will look like a ethene. It will have a structure similar to that of ethene. And so when I polymerize that, there will be a CH3 on each of the carbon atoms. So can you try one chloropropene? Yeah, just try one chloropropene. So to give you one chloropropene, and see how that comes wrong, how that will be. So the only naturally occurring addition polymer is rubber. And rubber, as you know, it is obtained from latex. So there are rubber trees that will produce something that is called a latex. On processing, it will give us rubber. So the monomer that is found in latex is actually this particular one, 2-methyl-but1,3-diene. So it has a methyl on this. So it's a but, as you just said, with 4 carbon atoms, 1, 2, 3, 4 carbon atoms, with double bonds on 1 and 3. The first carbon and the third carbon. And now that there are 2 of them, it is di. So but1,3-diene. Then there is a methyl on the second carbon atom. So this is the monomer from which you obtain rubber. So the rubber can be visually been obtained from that. So what happens during polymerization? This bond break, the electron gets to that, one electron there, the other electron there. So the result, these electrons that I've gotten here will form a double bond, but the other two, these electrons now can be used to bond outside. So this is a type of structure that I'll get. So the CH3 is right there with the double there. Now, and I can put, there is a hydrogen there, the CH3, and there are 2 such. So it will continue to bond outside. And that is what I've represented here. Now, because when you have a double bond, the type of bond that you have looks like that. So this double bond actually makes this molecule elastic. It's belong to the class of compounds that we call elastomers. It is elastic because if you pull it, it will straighten. It will straighten because of these bond angles. You apply stress on this side and the other side, it will straighten up. But if you release it, it will go back to, because this bond angle must be maintained. So it's an elastomer. So the double bond facilitate the stretching of the resultant polymer. Now, we could even call it poly-2-methyl-but1,3-diene, because that is a systematic way of naming polymers. So you realize that two molecules of the resultant polymer are bonded to each other by van der Waals. They are covariant, therefore we expect covariant bond between the molecules. Now that makes natural rubber soft and sticky. That makes it soft and sticky, and therefore will have very fuse. Like the stuff that you chew, the chewing gum. Chewing gum is actually rubber beef. Yeah, the sticky and the soft rubber. So chewing gum and tires are made from one and the same thing. It's only that the chewing gum has not undergone a further process. So, but can you use chewing gum to make tires? The answer is no. So what do you do with it? With the rubber, you react it with sulfur. So what will happen is that these two molecules are bonded by van der Waals, and that makes them soft and sticky, because van der Waals are easy to break. They are easy to break, so you can easily chew that. But that reduces its usefulness. So what do? When you heat it with sulfur, now you break this double bond, right? You break the double bond, you free an electron, you free an electron, you free an electron, you free an electron, you free an electron. So these electrons can be donated, not really donated, can be shared with the sulfur. Now, this one can also be shared with the sulfur. So we have a covalent bond between the molecules now. We now have covalent bond between the molecules. So we say we have a covalent cross ring. And because covalent bonding are stronger than van der Waals, then the molecule, the rubber now becomes hard. Unfortunately, that makes rubber impossible to recycle. You know, you cannot melt rubber. If you try to heat it to melt it, then it will decompose because you cannot break the covalent. You cannot break the covalent bond. This is the process, vulcanization. So it involves the conversion of the van der Waals cross ring to covalent cross ring via a sulfur. Looking at the uses of alkenes, so by now, of course, you know that alkenes are useful in making plastics. Now, when you talk, so all addition polymers will be considered to be plastics. And we have two types of plastics. We have some plastics that we call thermosetting. We have some plastic that we call thermosoftening. Thermosoftening. Now, a thermosetting plastic is one that you can only heat to melting once. So you heat it, you melt, you mold it, you cannot do that anymore. Now, such an example of such is melamine. If you try to heat melamine to melt, it cracks. It cracks. So because the molecules are decomposed. Actually, the idea is in the thermosetting, when it sets, when it hardens, it forms covalent bonds between the molecules. It forms covalent bonds between the molecules so that you cannot now weaken those ones. If you try to heat, they break, and so the whole structure will decompose. Now, thermosoftening are the types of plastic that can be melted and molded indefinitely. You can melt and it goes back to the solid state an indefinite number of times. Of course, the idea behind that is that it's going to have covalent, not really covalent, van der Waals forces between the molecules. Now, another use of alkenes is maybe in the manufacture of alkanols. Specifically, ethene is used in the manufacture of ethanol, as we shall see as you have already in the process that we call hydration. We've already discussed the hydration of the alkenes. So, ethene is used in ripening fruits. It is then the manufacture of detergents. The next thing is, so what are alkynes? Alkenes have single bond. Alkenes have double bonds. The alkynes now are hydrocarbons with at least one carbon to carbon triple bond. The simplest of the alkynes, of course, is going to be ethine with a triple bond, with a carbon to carbon triple bond, because you must have at least two carbon atoms. So this carbon has already formed 1, 2, 3 bonds. You need to add only one, because carbon must form 4 bonds. 1, 2, 3, so you only need to add one hydrogen. So that is the simplest of the alkynes that we call ethyne. It is C2H2. Now propyne, as has just been drawn, has one the triple bond. Then you put another carbon, 1, 2, 3, and then you need to add a fourth. 1, 2, 3, that's 4. You don't need to add anything. 1, 2, 3, 4. So those are all hydrogens. So C3H4 is the molecular formula of propyne. So to name alkynes, they'll add with ine. They will add with ine. So you have ethyne, propyne. But that is all that you can. That's a far that you can go that simple, because alkynes will also exhibit positional isomerism. So when you get to the The third one, that is butyne, you must specify where the triple bond is. So you must either talk of but1 ine or but2 ine, because there is ambiguity by just saying butyne. So the general formula of the alkynes will be CnH2n minus 2. Remember, if you want to have a triple bond, and you already have a double bond, maybe you already have a double bond, and that is CnH2n. That's what we said after we subtracted 2 from the CnH2n. Now to form a triple bond, you must remove those electrons so that the carbon can still retain its 4 electrons. So you need to subtract 2 electrons from there. So the general formula of the alkynes will be CnH2n minus 2. The preparation of the alkynes, we shall only, at this level, we shall only learn the preparation of one alkyne, and that is ethyne. It is prepared from calcium carbide. Calcium carbide, now if you were to write the expected formula of calcium carbide, it should be calcium valency 2, carbon valency 4. That is what you expect. So you cancel, so it's supposed to be written like that. That is what we expect to be the formula of calcium carbide. However, you can see how it's actually written. It's calcium carbide. So because at the end of the day, what I have is a carbon, is an ion that looks like that. It's an ion that looks like that. So the valency of that ion is 2, and this has, that is C2 with negative 2, and that cancels. So calcium carbide should be written like that. It should have the double. So when you react the triple bond, that is, when you react that with water, it will definitely give you calcium hydroxide and the ethyne. And this reaction is extremely exothermic. That is why you need to put a layer of sand that can absorb, it can absorb any heat that is produced. Otherwise, the reaction will produce a lot of heat, and the apparatus are going to crack. The chemical reactions of the alkynes, definitely, apparently it appears like all organic compounds burn. So they burn to produce carbon 4 oxide and water. If we have limited supply of oxygen, then you are going to get carbon 2 oxide. Now, again, as we said last time, the alkynes and the alkenes will all burn in a sooty frame. And that is due to the high percentage carbon. When you look at a compound that has 2 carbon atoms, the maximum number of hydrogen that it can have is 6. But these ones have 2 carbon atoms. So the percentage carbon is very high. It has a very high carbon ratio. Carbon to hydrogen ratio is very high. So it is not possible to oxidize all the carbon to carbon 4 oxide. Some of it is going to be emitted and oxidized, and therefore the frame is extremely sooty. So all alkynes, all alkenes will burn in a sooty frame. And this, of course, the fact that it burns makes it useful in use in welding. So because it is going to produce very hot frame, it is going to produce a very hot frame, especially when it's burned in pure oxygen. Then you will undergo addition reaction, but it's going to be stepwise. So the first step will lead to the production of a substance that has a double bond. Then after that, the substance with a double bond will now react to form a substance that has a triple bond. Now, for instance, hydrogenation. Hydrogenation refers to the reaction with hydrogen. Now, in the presence of a nickel catalyst, at temperatures between 150, temperatures of about 150. You remember that the other substance reacted, the alkene reacted at temperatures of above 180 to 250. This one requires lower temperature. Now, why is that so? Because when you look at this bond, there is a concentration of electrons here. There's a concentration of electrons around that triple bond. Now, the electrons being negative repels each other, and that actually ends up weakening that bond. So if one of the bond requires 349 to break, then 3 of them are not going to require 3 times that, 1050 or around that. They're not going to require 1050 because the repulsion between those electrons will end up weakening each of the bond so that they are not all equally strong. So if the first thing that will happen if you add hydrogen to that. Remember, using nickel cartridge at 150, that will lead to the formation of, if that is propyne, that will form a substance, the double bond. And so the triple bond has already been, the third bond has already been broken. And when the third bond breaks, that is the structure that you have. Then you add the hydrogen. You add the hydrogen, one there and the other one there. So that is a propene. Now propene also can undergo further hydrogenation in the presence of nickel catalyst at now temperatures between 180 to 250. That will lead to formation of propane, as we saw in the previous discussion. Now the other reaction, so a halogenation, of course, is the addition of a halogen, and you can still add the solutions or the solutions in water or the solution in organic solvents. If the reaction will definitely be faster, because as we have just said that these bonds are weaker. So if you want to distinguish between an alkene and an alkane, and an alkyne, maybe you can look at the rate of the decolorization of bromine water, the rate of decolorization of chlorine water, the rate, but how do you actually measure the rate? Now, so this will lead to the formation of the substance in the double, and you can try this. Try the reaction between bromine dissolved in tetrachloromethane. Now the third bond is going to break, and what do you get? A structure that looks like that without the third bond. Then you attach a Br, no, sorry, it did have two hydrogen. So that is what, then you attach the Br on both on adjacent carbon atoms. Then you can do the second. So we have already looked at that. Then you can add bromine to that again. It will lead to the formation of that is what you now have already. That is what you have already. You attach bromine there and bromine there. I think that will be 1122 tetrabromoethane. 1122 tetrabromoethane is the name of the product. Of course, if you have excess bromine, there is no reason why substitution cannot take place. There is no reason why substitution cannot take place if you have excess bromine and you are doing the reaction in the presence of sunlight. So you can get the hexabromo. The hexabromo ethane can also be obtained. Next, the reaction with hydrogen halide, what you can refer to as hydrohalogenation. And you have an example here, plus hydrogen bromide, that will lead to the formation of the substance without the third bond. Then attach H here, and then attach bromine there. It's hydrogen bromide. Then I can still continue adding more of the hydrogen bromide. Break now the double bond. I already have that HBr. Note the hydrogen can either attach itself here or here. But remember the rule that you gave, hydrogen will attach itself to where we have more hydrogen already. So the main product is going to be 1,1,1,dibromoethane rather than 1,2-dibromoethane, because the hydrogen prefers to attach itself to where we have more hydrogen already. We wind up this by just looking at the uses of alkynes, the manufacture of adhesive and plastics. If you want to prepare chloroethene, maybe the first thing that you will have to do is react ethane with hydrogen chloride. Then you get chloroethene, then you can polymerize that. So you can use it to manufacture plastic. It is used to manufacture synthetic fibers like rayon, and ethane is used in this is a familiar use, the oxyacetylene frame in welding. That brings us to the end of the organic chemistry one, where we have looked at the three homologous series, that is alkenes, alkynes and alkanes, all of which were hydrocarbons. So hydrocarbons, as we said, are compounds of carbon and hydrogen only. Now the alkenes, all of them will burn if you are, now they will all share the physical properties. The physical properties are all the same. They don't dissolve in water because they are non-polar, but they dissolve in organic solvent. Number two, their melting point and boiling point are dependent on the size of the molecules. That is as far as the physical properties of all the hydrocarbons is concerned. Now, when you talk about the chemical properties, they all burn, but the nature of the flame now differ. The alkanes may burn in a sooty or a blue flame, but all the alkenes and alkynes will burn in a non-sooty flame, in a sooty flame, that is. Now the alkanes will undergo substitution reactions in the presence of sunlight, whereas the alkenes and alkynes will undergo addition reactions. They will undergo addition reaction.